Hey everybody, it's Mr. Klein here. Unit 7, Lesson 6, the volumes of prisms and cylinders and Cavalieri's principle. Okay? So what we're going to start off with here is we're going to start with example 1, where we have a right triangular prism and a box or a rectangular prism. So it says here, the bases of the following triangular prism T and rectangular prism R lie in the same plane. A plane that is parallel to the bases and also a distance of 3 from the bottom base intersects both solids and creates cross sections T' and R'. So what I'm going to do, ladies and gents, is I'm going to start with A and C on the left-hand side. The first question is find the area of T'. Well, we know that this is a triangular prism, and so we know then that the area of the base is going to be 1/2 base times height. That is just the area formula for a triangle. Now, the area is 1/2 times, well, we got to be careful. What is the base of this triangle? Remember, the base is where it meets a perpendicular with the height of the triangle. If we're talking about this blue triangle T' here, right, that's what we're finding the area of, we can go up to the base here. And if I look right there, that red perpendicular is the height of the triangle. Again, if we're thinking of a triangle, I'm going to draw it out like this. The height here in red is 3.3. That's that perpendicular. And the base then is 10. So the base will be 10 times 3.3. And when I do this, the area of that triangle is going to be 1/2 times 10 times 3.3, which should be 16.5. Okay? Part C asks you to find the volume of T. So remember from last lesson, the volume formula for any prism is capital B times H, where capital B is the area of the base and H is the height of the prism. Well, looking at this, we already have the area of the base. That's what we solved for in part A. So we know that the area of the base is 16.5. The height, in other words, the vertical height of the whole prism, is 5, because this here is the base, and so this is like the depth of the triangle, which is just 5. If you notice, they gave us a lot of other different measurements here, but a lot of those measurements were actually useless. We didn't need them for our problem. And so when I do this, my volume here is going to be 82.5 cubic units. They didn't give us any units, so we'll just leave it at 82.5. Okay? All right, let's go over to the right side there with the rectangular prism. They want to find the area of R'. And so again, the area of R' there will be the length times the width, which for us is 4 times 4.125. When we do that, 4 times 4.125 is going to be 16.5. And so to find the volume, just like last time, volume is capital B times height, where capital B is the area of the base. So we know that the area of the base there is 16.5, and the height of the entire prism is 5. This looks very familiar because this is actually the same calculations from last time, and so thus my volume is 82.5. So this isn't a coincidence. As long as two three-dimensional objects have the same area of the base and the height, then they'll take up the same amount of space, i.e. volume, even if they don't look like each other. Okay? So it then says, if a height other than 3 were chosen for the cross-section, would the cross-sectional area of either height change? For instance, say that we went up 4 units instead of 3. Well, no. The cross-section wouldn't change. It's still the same object there, and still the same cross-section because of the fact that it is a right prism. So no, the cross-section won't change. That's it. If you want to write because it is a right prism, that is fine. All right. So this kind of brings us to the main topic of this lesson, which is called Cavalieri's principle. Okay, Cavalieri was an Italian mathematician, but Cavalieri's principle in 3 dimensions says this. Suppose two regions in 3D space, which are solids, are included between two parallel planes. If every plane parallel to these two planes intersects both regions in cross-sections of equal area, then the two regions have equal volumes. That is a mouthful, but it's probably a lot easier to look at an example. For instance, below, on the left-hand side here, each of those brown shaded objects has the same cross-section area. And we're also saying that the heights of them, i.e. the vertical height, is the same. So, as long as the cross-section areas are equal to each other and the heights are the same, even though these objects are kind of topsy-turvy and they're curved, they actually have the same volume. So all three of these have the same volume. Likewise, over here on the right-hand side of the page, both of those green cross-sections have the same area, even though this one is a rectangle and this one is a trapezoid. But they have the same heights, and so because they have the same area for each cross-section, and the heights are the same throughout, then these two volumes are equal to each other. And that's it. That's Cavalieri's principle. Let's look at an example of this with coins, because I feel like coins are probably the easiest way to see these, and if we were in person in class, that's how we do it. So check this out. You're given two stacks of quarters pictured to the right. What do we know about their volumes? Are they equal? Are they not equal? And why? Well, imagine that you have a stack of coins as such, and you just kind of push them all a little bit to the left or a little bit to the right. If you took the volumes of the original stack and the new stack, they have to be the same. You didn't change anything about the coins. We know the volumes are equal. So those volumes are equal to each other. But why are they equal to each other? The volume of each slice, and I'm going to use air quotes around that, each slice are equal to each other, or each coin, I should say, are equal. Thus, no matter how you orient them, the volumes are equal. Okay? So it's really important to know that. Another way that you could even describe it is that the cross-section is the same throughout. So by Cavalieri's principle, they'll be the same. So by Cav principle, the volumes are equal. Okay? But that's Cavalieri's principle, and I think with coins it makes a lot more sense rather than talking about it abstractly with prisms. Okay? So number 3 says, Morgan tells you that Cavalieri's principle cannot apply to the cylinders below because their bases are different. Do you agree or disagree? Explain, right? So Morgan's telling us that Cavalieri's principle cannot apply to the cylinders shown below because their bases are different. Well, hold on a moment. Let's go back to the other example down here, right? Let's look at those bases here. This base here is a square, and this one is a trapezoid. The bases weren't congruent to each other, right? In other words, they weren't the same shape, but we did find out that they have the same volumes. So it's not that it can't apply because the bases are different here. However, in this specific case, the areas of the bases would have to be the same. So it could apply, but we would have to know that the areas of the bases, i.e. the cross sections, we would have to know the areas of the bases, that is the cross sections, are the same. Okay? And that's it. So I would say I would disagree with Morgan. It could apply as long as we knew that the areas of the bases are the same. In this case here, the chances are it probably isn't. And so then Morgan's probably right, but her reasoning, or their reasoning, I should say, is that the bases are different, thus you can't use it. And that's not true. You can only use it if the bases are equal to each other in area and the heights are the same of the objects. So we'd also have to have the same heights as well. Okay? All right, everybody. So I hope that kind of makes some sense. If you have any questions, please feel free to ask them in class tomorrow. But if not, have a great night and we'll see you tomorrow. Have a good one. Bye-bye.